So my name is Murad, and I'm going to talk about the switch-based multicast. So multicast is a mode of communication where one sender can send to multiple receivers by sending only one copy of the message. And with multicast, we can obtain higher bandwidth and utilization of the network, in addition to lower latency, because now the sender will send only one message instead of many copies. Um, so emerging multicast with open MPI will have a great improvement for the acceleration of the following functions that today is they work in a mode of point-to-point. So for example, in MPI Bcast, the root will send a single message to the multicast group, and the switch will distribute the message to all other group members who wish to listen to the multicast group. In MPI Allgather, for example, each node will send its own data in one message to all other group members. The same with MPI Scatter and all-to-all, but here, like each node will take its own part of the data, and like it's much faster, but each side might receive redundant data, but we should consider like the trade-off between latency and redundant data here. So I'm gonna talk about how to join a multicast group. There are two parts. One in the switch, we need to notify the switch about the listeners. So we need to send a request with the IP add membership to IGMP routers, which will enable the switches to forward packets to the correct devices in the network. As you can see here, like in the image, like this group number, every packet that arrives with this IP will be forwarded to port number 11 and 5. And also we need to join the multicast group in the host so that the NIC would know that where to forward the packet to which QP. And today multicast works only with UDQPs, and currently is working with Rocky V2 because of a bug we found on a switch while running Rocky V1. But now it's being fixed by the switch vendor. So we're waiting for a fix in order to run Rocky V1. So in order to attach a QP to a multicast group, you need to run IBV attach MCast. And with that, all packets with that group will be forwarded to the QP. We might add like a little challenge here. We need to make sure that all ranks are attached to the multicast group before the first send of the data. Otherwise, all the packets will be not delivered.
So that begs a question. Right? I mean, since it's on a UDQP, you have to implement a reliability protocol.
Yeah,
correct?
yeah. I'm gonna talk about it in the next slides. Um, so um, so in order to send and receive multicast messages in UCX, we created a new interface for multicast, which inherits UD MLX5 and UD verbs, which are already implemented and working with point-to-point. And we kind of overloaded some part of its operations, as shown here, to um, make some um, changes for the packet address and all that stuff. So now with this kind of implementation, the multicast interface, UDMcast ML5, can send with multicast IP and with point-to-point, both. So all the messages will be, like for the root, will be sent over the multicast address, and the ACKs, in order to support reliability, will be sent over the point-to-point. That's a figure of how the endpoint would look. Today, like UCX was built or was designed to support point-to-point communications. And since we only have one message to send to all receiver, we need to allow one-to-many connection for an endpoint. And in order to support reliability for collective operations. So this is an example of multicast reliability, which we will implement in the software. So for example, here, the root sends a message, a multicast message to with PSN5 to the switch. The switch will distribute the message to A and B and C, but suddenly C didn't get the message and it was dropped. Later, the root got the ACKs from A and B, but not from C. So here we have like an array that shows us which ACKs were received from the receivers. And after a timeout, like the root will resend all the messages that were not received to all again, like in a multicast. This is the results we got for MPI Bcast for message size 32 bytes. It's still under implementation, but we got results for this for now. And we got really good results for number of processes 8. We got 63% of improvement on latency compared to point-to-point. And as we can see, the more we have receivers or ranks on different hosts, we will save a lot of latency. That's it. Any questions?
Can be questions about both parts if you want.
Any questions for Alex and Morad before I ask my questions?
Yeah, Alex and Morad, thanks. So I wanted to see like what should be the takeaway, or is the takeaway that we have to make a multicast as a basic primitive where we have to build the collectives? And that's first question. And the second question is like, have you studied using this in workloads where the workloads are more bandwidth sensitive, and collectives like all-to-all large message, something like that, right? What's your opinion on that?
So, so for the first question, yes, we clearly think that one-to-many and many-to-one should be addressed. Like Morad kind of mentioned it, and I even kind of went around it, but since UCX is designed for point-to-point, we kind of had to hack it to have this one-to-many logic, and we feel like it should be a first-class citizen, especially if we're talking about collectives. But the takeaway wouldn't even be that. The takeaway would be that it makes a lot of sense to look into the way the internals are implemented, because there's a lot that can be shared. So I for one feel it's a pity that you would usually see one-to-many and one-to-one in separate modules, and they can't share data structures and the code across. And as for the large workloads, Morad, sorry for hogging the answer, but actually we don't have it stable enough to have reached that far. So this is still under development. And actually, Morad worked very hard to have it in time for this talk. So I appreciate his effort, but we're not ready to present more results simply because we don't have them.
Okay, thanks. So say that if we are designing new shared memory transport for a system, right? Obviously, you guys have more experience with 256 cores, so that is coming with you, right? Do you recommending that these system implementers go provide a shared memory transport that has to be multicast as a primitive?
Who do you mean in your question? I'm not sure I understood who should provide.
No, if
clearly
somebody,
it should. Yeah.
If somebody is listening to these two talks, right, and say that I want to build a system, shared memory system, right? Should these developers, these system implementers, right, hardware particularly, should we support this as a multicast as a primitive, as a basic primitive?
Yes, I mean, I believe so, but I'm obviously biased because this is what I do for a living. You wouldn't be surprised to know we approached the guys in the more low-level departments in Huawei and told them, look, this is a requirement, and they just added it to their requirement list. So I don't know what will become of it, but yes, clearly for our line of work, this kind of operations is what we would call a primitive. Yes.
Okay, because this kind of exists in say network hardware level, right? So
yes, I agree.
Yeah. Okay. Yeah. Thanks.
Alec, so am I understanding it correctly that your aim is to have like really high performant shared memory collectives for like highly multi-threaded nodes?
Yes, we have. They call them, the marketing calls them high density servers. So yes, these high density servers with 256 processes should have their own good shared memory capability. Otherwise, we're doomed.
And the goal is to get some kind of like what? So I'm curious in your measurements, for example, like with Allreduce, because it's completely agnostic of CPU architecture or anything, right? It's what would be speed of light?
What do you mean?
I mean, how
I'm
fast?
not sure I follow.
Can you do a reduction on 128 cores? How fast should you do a reduction on 100?
So clear. So that depends on a lot of things, obviously. But we have the numbers, if I recall correctly. Let me look it up.
I mean, again,
we reached.
I'm not saying it needs to be right now. I'm just saying it would be interesting to see that in the context of what speed of light is. How where are you? On each incremental phase of development, are you getting progressively closer to that target?
Yeah, well, at I don't know, like a ballpark of 5 microseconds, I'm not sure we're quite at the speed of light yet, but obviously it's about reducing this number as much as possible, and the hardware engineers do most of the work. I just kind of code it differently.
Well, I mean, that kind of begs the question, though, right? Is this semantically the right?
Well, then
performance is so sensitive, especially for small data, right?
Mm-hmm. Yeah, but I mean, what's the alternative?
Mapping, message passing on top of shared memory introduces a lot of overhead.
I agree, but we're kind of bound to the applications and what they use today. It's not like if we invented something new, everybody would automatically transition to it. So we're kind of limited here.
Yeah, but I mean, under the covers, in your implementation, though, right? I mean, you're implementing it with two-sided with a two-sided API, if I understand.
Mm-hmm. Yes, we are. I mean, we're open for suggestions, but it's very hard for me to see right now, like if we even change our implementation to have some different semantics, how would an application trivially transition to that new model?
No, I mean, I'm just saying, if you're running, how do you expect someone to use this capability? I mean, isn't it? I mean, under the idea is to still support just basic MPI collectives, right? I mean,
right.
Nothing changes from MPI application perspective. You're just saying, you're going to add some more bells and whistles that should, expose more, performance opportunities, right, underneath the covers.
Yes.
And the MPI application just gets the goodness of that, right? But your implementation, you're implementing, this optimized shared memory transport over a two-sided programming model, instead of like loads and stores, which would be the native transactional model, right?
Yes. I think I see where you're going, but this is what we have today.
Well, I mean, that can't be right.
Can I ask what you call two-sided and shared memory vs load and store? Because like eventually load and store is used for either way. So what is two-sided?
Yeah, I mean, is there explicit synchronization, right? I mean, if I'm a leaf and I'm putting data into the slot on a fan-in, like a reduced fan-in, right? How do I? Is there explicit, synchronization between the two processes in a two-sided way, or is he just like pulling on memory?
I think it's just pulling on memory. If this is the question, it's not really right, Alex.
Yes.
It's regular FIFO, shared FIFO. So you have synchronization one in K. Sense, but it's just pulling on memory. So there is no, in this sense, I don't think there is explicit synchronization.
No, there is the locked. There is the locked mode, but as I mentioned, it's probably good only for large messages. I tested it once, but I didn't even provide results because we focused on the small messages, which is polling.
So it is in this sense, I think, just to sort of synchronize on terminologies that we use. In this sense, it is one-sided.
Okay.
It uses FIFO.
Yeah, I'm just saying, like, it's we can regale you with many stories about the perils, the agony and the ecstasy of shared memory programming. So it's.
My other comment, Alex, so thank you for doing this many core. It's kind of really important to our. We have more and more vendors building SOCs with a lot of cores. Like Ampere, I think 128, and they have multi-socket cores per 128 per single socket. And I think we'll see more. So it's very important. My general question, we have 3 minutes left. What is so you extending UCT?
Mm-hmm.
How you envision is the idea to upstream at some point in UCX? And
yeah, that's a painful point. Actually, that relates to the other thing I wanted to tell you. I happen to know the speaker from the next slot, and he's willing to give a bit. He's willing to delay a bit, so that's fine. What I am going to say is I am going to talk about this also in the context of the next talk, but basically it would be very hard for me to yank it outside the UCT because it really shares code. We actually like shamelessly made some static functions in shared memory non-static, so we could include them from that code. And Morad did the same for UDMLX5. So that's like it is really most of the code we added, like for every piece of code we added, we use 10 times that code existing in UCT. So it would be very hard for me to see a way to upstream it outside UCT.
It's kind of my experience. It's similar when in Cheetah we implemented like everything. You probably saw this B calls, which it was like 90% duplicated tiered BTL code, right? Which is, looking back, it was bad choice, but it was driven by project politics, not by engineering. So it's worthwhile to have this discussion. You know, it is big change for UCT because we don't expose today collective APIs.
So actually about that, I kind of said I didn't change the UCT API, and then I went back and said I changed a lot of things in UCT to make it work. Actually, if I want to say just the bottom line, we only changed the capability structure. We didn't actually change the calls. So both Morad and myself, we use short bcopy and zcopy send for our implementation. Active message, that is. So it's not it's not breaking anything in UCT API per se. It's just changing its mission statement. So it's a big change, but not code-wise. Not a big change, but not necessarily code-wise.